Hello, and welcome to my poster, Modeling the Thermal and Chemical Evolution of the Martian Lithosphere Through Time. My name is Rose McGroarty, and this is the research that I've done for my master's thesis. The motivation for the study is that there are currently few constraints on Martian evolution. And so we have decided to develop a self-consistent model that will explain the Martian lithospheric evolution. And we've decided to do this using a combination of geochemical and geophysical methods in order to help us better understand the planetary formation from both geophysical and geochemical perspectives. A little bit of background information about Mars. Mars' surface has been studied by rovers and satellites. We've also used meteorites as a way of obtaining samples from Mars because we have not yet returned any samples from the planet's surface. And so we know that the crust is about 50 kilometers thick on average, and this has been inferred from orbital gravity measurements. The actual thickness of the crust ranges from about 3 kilometers thick to over 100 kilometers thick, but the 50 kilometers is the average thickness. We also have mantle potentials, potential temperatures that have been calculated by Filiberto. And so we know that there's been a trend of cooling through the mantle from about 1,450 degrees Celsius 4 billion years ago to 1,345 degrees Celsius in the present day. We know that there has been significant melt generated in the past, and we know this because we see volcanoes all over the surface of Mars. And so we can tell that there has been extensive melt generated and that has erupted on the surface through volcanoes. And so we constructed models using surface and experimental data. And so we used the mantle composition from Jarvis and Venke. We used the average crust composition, and we used the radioactive decay of heat-producing elements. Figure 1 shows a schematic of the Martian interior. Drawn to scale are the crust and Martian and mantle lithosphere. Not drawn to scale are the convection cells in the mantle. I also put an image of the InSight lander because originally we had intended to use the heat flow from the HP3 probe on the InSight lander. So geochemically, our methods first included calculating aerotherms, and these are temperature profiles through the crust and mantle lithosphere. So these were calculated according to the equation presented in section 3. And we used the surface temperature of 220 Kelvin. We used an estimate of the thermal conductivity. We used the surface heat flow, and then we also used the depth and the heat production from the heat-producing elements, uranium, thorium, and potassium. We calculated these aerotherms in billion-year increments. And we started with a surface heat flow today of 25 milliwatts per meter squared, and 4 billion years ago of 50 milliwatts per meter squared. The crustal thickness today is about 50 kilometers. This is a global average. And 4 billion years ago, about 20 kilometers global average. We used the adiabats, aforementioned from Filiberto, in order to, the mantle potential temperatures from Filiberto to show the adiabats today. Some of our assumptions included that the planet was initially homogeneous and that there was an undepleted crust and mantle lithosphere and that there was uniform heat distribution. And so we calculated the melt fraction at each time step. To calculate the melt percent, what we did was we calculated using the equation that is also in the geochemical methods. And so what we did to calculate this is that we used the pressure at the point where melting began, which was the intersection between the solidus and the adiabat. And we used the pressure where melting stops, which is the intersection of the aerotherm and adiabat, which is the base of the lithosphere. We also calculated the temperature at which melting occurred, which is the temperature slightly off of the solidus line where the melting took place. And then we used the melt percent to calculate the melt model. And so to calculate the melt model, we used experimental data from Collinet and Matsukage, and that showed the partitioning of oxides into melt, minerals under pressure and temperature. And so what we did was we took the data from these experiments and we fit an equation to them using least squares minimization. And what these equations give us is the weight percent of oxide in the melt at a given pressure and melt fraction. Our geophysical methods included calculating aerotherms using using spherical 3D solid-state convection using SITCOM-S. These calculated the average mantle temperature over time and include conductive and convective components in the aerotherm. So these aerotherms go a little bit deeper than the aerotherms that we calculated geochemically, because geochemically we stopped the aerotherm calculation and then simply incorporated the adiabat calculation, whereas the SITCOM-S did the entire calculation from the surface to the core mantle boundary. We used variable internal heating, which was a proxy for time, and varied the core fraction of the planet's radius to account for whether there was a high amount or low amount of sulfur. And so from this, we got the average surface heat flux and melt fraction through time. And we compare this to the geochemically derived values to produce a self-consistent model. So our preliminary results, figure 2 shows the geochemically calculated aerotherms. And the darkest line represents the present day and the lightest line represents 4 billion years ago. The solid lines are the aerotherms and the dashed lines are the adiabats. And the black solid line represents the Martian solidus. And so we can see from these aerotherms that there was a great deal of melt produced 4 billion years ago, because there is a great difference between the intersection of the solidus and the adiabat and the intersection of the aerotherm and the adiabat. However, in the present day, what we see is that the intersection of the aerotherm and adiabat occurs before either cross the solidus, and so the present day aerotherm never crosses the solidus. And what this tells us is that on a global average, there is no melt being produced on Mars. Now, this does not take regional factors into consideration, and so it is certainly possible that there could be melt produced in local areas, but on a global average, there is no melt being produced on Mars, aka there is no magma ocean on Mars. Our geodynamic aerotherms in figure 3 show the calculated planetary average aerotherms for a 0.45 core fraction, which is a higher sulfur core fraction. We also have the Martian solidus plotted in black. Now, what's interesting about the geodynamic aerotherms is that right now they actually do not cross the solidus, and this is because they are global averages. And so the reason why there is melt production associated with these aerotherms is because SITCOM-S took the amount of melt that could be produced in local areas and summed it in order to get a global average melt. And so that's why there is a melt tied to these aerotherms, even though initially they're not crossing the solidus. And this is something that we intend to continue to address as we plot these aerotherms. Figure 4 shows the melt model compared to the data. And so this is where we took the data from the Colony and Matsukage experiments. And this is only for silica, because this is just an example of how we fit the model to the data. And so we took the data and we divided it into pressure bins for ease, and also to show how the data varies by pressure. And so we then calculated the line that best fits the data. And so we've plotted the data as well as the line that best fits the data. And so that is how we derived the melt model. And then figure 5 shows the results of our melt model. And so we can see the melt percent over time, and our purple diamonds represent the geochemically calculated melt or oxides, and the yellow circles represent the geodynamically calculated melt or oxides. And so we can see in this plot how silica has decreased as melt has decreased geochemically. However, interestingly, there is a disparity between the geochemical and geodynamic data, where the geodynamically calculated silica is actually increasing with melt. We also show the iron and the aluminum. We have calcium, magnesium, potassium, and sodium all plotted in these melt model results. And so the implications at this point are that as the planet is cooled over time on average, the crust in the lithosphere have thickened. This is evident in figures 2 and 3. The melt production has also decreased, and the composition becomes less silicic with time. The geochemical melt fraction, on average, there is no melt predicted today. The geodynamic melt fraction is summed over all the hotspot melting, as I said before, and so the average temperature is below the solid S, but this is also taking into consideration hotspot melting when calculating the melt fraction. And so these results help show us how the early Martian thermal and chemical evolutionary processes have occurred. And it's telling us how this planet has changed both compositionally and thermally over time. The next steps for this research will be to recalculate the aerotherms to account for calculated crust and mantle lithosphere compositions. And so taking into consideration the fact that the HPEs are no longer in the depleted mantle lithosphere, we will adjust the aerotherms and recalculate. And we will also calculate the aerotherms to find out when the last stage of melting occurred on average. We also will refine the error to make the error a little bit better constrained. And we'll tie the geochemistry and geophysics together self-consistently so that we have a better idea of how the planet has evolved in the self-consistent model. Thank you very much for attending my poster, and please feel free to contact me. My email can be accessed through the contact author, and I'd be happy to answer any questions you have. Thank you.